Okay, for the RF2 function here, we've made an attempt to sketch and indicate the way this function behaves in space, the path traced out by this vector in space. And we've calculated the derivative of r. We've calculated the unit tangent vector by dividing the derivative of r by the magnitude of r, and we got this expression. Now we need to take the derivative of the unit tangent, and that's going to give us a vector in the direction perpendicular to the curve, and then we're going to have to divide that by its magnitude, which is not difficult to write down, but it gets kind of messy and algebraically challenging. So we need to take the derivative of this function. Now, to take the derivative of this function, I'm going to come back to the form r prime of t over magnitude r prime of t, and just write down the derivative of this expression, understanding that r prime of t is the function that we've already obtained. So I write unit tangent vector t prime of t is r prime over magnitude of r prime prime, applying the rule, the quotient rule, which does apply to vector functions and scalar vector function divided by a scalar function. We find that the derivative is r prime prime times the magnitude of r prime minus r prime times the magnitude of r prime prime. In other words, if this is f over g, f prime g, which would be this, minus f g prime, which is this. And then, of course, that would all be over the magnitude of r prime quantity squared. Now remember, r prime is something we've already calculated right here, so we can use that expression for r prime. And this expression here just represents, okay, again, we've got r prime over magnitude of r prime. So it's just the derivative of the numerator, which is the r prime, times the denominator, minus the derivative of the denominator, which is magnitude of r prime, times the numerator, then divided by the square of the denominator. If we were just looking at this expression, we would probably write it out similarly. And that's going to come out. I'm going to switch to a smaller pen here, or sharper pen. Okay. Negative 27 cosine of 9t prime times I minus 63 sine of 9t prime times j plus 2t quantity prime times k, where the prime indicates derivative with respect to t. And I'm not going to get that all in one line, but then it's going to be minus the r prime, which is just our negative 27 cosine of 9t I minus 63 sine of 9t j plus 2t k, multiplied by the derivative of the square root of 27 cosine squared of 9t plus 63 sine of 9t quantity squared, and I got my square in the wrong place there, plus 2t quantity squared, all that prime. And then we close off our brackets, something I probably haven't left myself enough room to do. And then we divide that by the magnitude of r prime squared. And we get a little bit of a break there because r prime is just a square root, so we're going to write down quantity 27 cosine of 9t quantity squared plus 63 sine of 9t quantity squared plus 4t squared. Okay, so now all we have to do is take derivatives up here and complete our expression. And I'm not actually going to do that. I'll work this out on the side, write out the result, and it's very straightforward. This derivative's easy. We've already done derivatives like this for an arbitrary function or another function where we had an omega t instead of a 9t. The process is going to be very similar to what we've already seen, and I don't see a point here in going through the whole process and taking time to do the video. I don't mind taking the time to do the video. I'm going to have to spend the time to do this anyway, but there's no point in doing it on camera.